Okay, so this video is about a few properties of this really intriguing family of self-intersected four periodics in the elliptic billiard. As you know, there's another family that is non-self-intersected in elliptic billiard, and these are parallelograms that are inscribed in an ellipse and circumscribe a confocal ellipse. But in the case of the self-intersected n equals 4, the caustic is this confocal hyperbola here, represented by these two brown branches. So let's look at the family. I'm driving it, I'm traversing it by defining the position of this red point here, and then because this is the elliptic billiard, I'm just going to hit against the boundary, and at every iteration I'm going to be tangent to one of the two branches, and I'm just going to hit the boundary and be tangent again and repeat and repeat and repeat. So I'm going to get this kind of a progression. So this family has two singular configurations. This is one of them, where you're basically going off to this point, exactly where the hyperbola intersects the ellipse, and the normal here is facing the red point. So I'm going to go forth and then come back in the same direction, and I'm going to repeat this. So this is a degenerate four periodic where the back and forth in either one of the two arms coincides. So if I leave this position here, and now I'm going to place my red at this other position here, where that red dot now is over the asymptotes to the hyperbola, I get a symmetric configuration where the diagonals pass through the center of the ellipse. And I have a third position, which is similar to the one we just saw. I can't quite get to it, but it's a position that will look like this, except that I'm going to be flipped along y, right? So if if the red vertex gets pretty close to that asymptote right there, actually not to the asymptote but to the intersection point, I invert along y, or I flip that degenerate doubled up configuration along y. Okay, so I have this. Now what are other interesting properties of this family? Because this is an elliptic billiard family of four periodics, its perimeter is constant. So I'm showing the perimeter up here, 8.2327. It's going to be constant. The signed area of these self-intersected shapes is exactly 0. Why is that? That's because this triangle here, traversed in this direction, is symmetric and has the same area as this other triangle here, traversed in the opposite direction. The other interesting thing about this family is that the sum of cosines of its internal angles is conserved. Now we've proven that to be the case for all n periodics. If you actually do the sum of internal cosines for its non-self-intersecting cousin, the family of parallelograms, that sum of cosines is identically 0. But in this case here, it actually has a finite positive value. Okay, and it's constant. Okay, now what are lesser known properties of this family? Let's try to draw a circle that goes through three of its vertices. So I'm going to pick this vertex, that vertex, and this vertex over here. 3 points define a circle. So I'm going to draw a circle that passes through these 3 points. Let's do it. As soon as you do that, you notice a miracle. Dynamically, the four vertices of this family are concyclic, and they're concyclic with the foci of the outer ellipse. Actually, these two foci are common to both the ellipse and the confocal hyperbola. So we have this really interesting situation here. Okay, now because they're concyclic, imagine now inverting these four vertices with respect to a circle that is sitting right at the left focus. Okay, so I have a circle here. I have actually 4 points that lie on a circle that pass through this focus. Now I'm going to invert these 4 points with respect to a circle that you cannot see here, centered on this focus. What do you get? You get 4 points, these 4 pink points here, which lie on a segment. A well-known property of inversions of circles with respect to a circle whose center contains the original circle is that this dashed blue circle here is going to be sent to a line, to an infinite line. So any points on that circle are going to be sent to points on that infinite line, and here they are. It turns out that if you traverse this pink degenerate polygon, inversive polygon, in the order prescribed by the original polygons, its length is going to be, the perimeter of this degenerate pink polygon is also invariant. So you can see here that the perimeter of the degenerate polygon, 5.0881, is invariant. Okay, now let's turn to another final fascinating property of this family. I'm going to turn off the inversive. Actually, you can see the inversion circle right here. Here's the inversion circle. So I'm inverting the blue, or the set of four periodic vertices with respect to this dashed black circle centered on the focus, and then you get that line. Okay, all right. So let's go to another property. I'm going to now draw the midpoints of each one of these trajectory segments. So I'm just going to take the midpoint, the midpoint, the midpoint. What happens? These four midpoints are collinear, and they're collinear along a horizontal line, or a line that is parallel to the major axis of both confocal conics. So that's pretty interesting. What is the locus of each one of these 4 points? What's the common locus, actually, of these 4 points over the family? Here it is. It's this beautiful H-shaped curve. So as I traverse the family of 4 points, which remain collinear along a horizontal line, they're going to be traversing this H-shaped curve. If I change the aspect ratio of my family, I cannot do this completely freely. I'm going to get a different H-shaped curve. Right now my aspect ratio is at 2.18. If I go back to, say, 1.5, oh, it doesn't let me go to 1.5. Maybe it wants to go to 1.6. It doesn't let me go to 1.6, so let's go back to 1.8 and hope that my numeric errors cease to exist. Let me delete them. This happens at every demo. This is probably because I'm drawing this locus as well, and it's not so stable. Okay. So, yes, there's one more thing. Let's consider the so-called excentral polygon with respect to this guy here. So, this is a bigger polygon. It has sides which are perpendicular to the bisectors at every vertex. So you get this kind of green polygon here, which would be sort of akin to the excentral triangle of a normal triangle. So its sides are, let's make that a little bit bigger. Its sides, each one of its sides is perpendicular to a normal or a bisector of each one, because this is billiard, so they coincide, right? So the normals to the ellipse coincide with the bisector. So here's my excentral polygon to this family. Okay, that's a pretty interesting object as well. Now, its 4 vertices are also concyclic with the foci. Let's see if we can look at it. I'm making this image a bit bigger, a bit smaller. So if I draw the circle that passes through 3 vertices of the excentral polygon, we're going to notice that the 4th vertex falls on a circle as well, and that this circle is also concyclic with the original foci. So it's really quite an interesting source of interesting properties. All right, I hope you've enjoyed it. Thank you.